name is Connor, and today I'm going to be helping you solve a problem of related rates. Let's read the problem. So two cars are initially 1,200 miles apart, and at the same time, car A starts driving at 35 miles per hour to the east, while car B starts driving at 55 miles per hour to the north. Here's a sketch of that situation. At what rate is the distance between the two cars changing after A, 5 hours, B, 20 hours, and C, 40 hours of travel? So what we're going to do in order to solve this problem of related rates is you can see quite clearly that a car moving eastward towards the initial position of a second car moving northward creates this pivot point. And as we calculate the distance between the two cars, even though it is changing, we see a triangle appear, which means that we've been given the opportunity to use the Pythagorean theorem in order to solve a problem like this, and that's exactly what we're going to do. Additionally, because the goal here is to measure the rate of change of this distance between A and B, we need to take the derivative of this value, which will eventually be called C. As you can probably guess, we have car A and car B fill in the other two roles in the Pythagorean theorem, which, if you don't remember, is C squared equals A squared plus B squared. That, on top of taking the derivative in order to calculate the rate of change, is exactly how we're going to solve a problem like this. All right, so we need to begin by defining our other two variables, if not just generally, because we know this distance is C, and we know this distance is A, and this one will be B, and I'll just fill that in. But we have a little more information as to what, I'm sorry, this is supposed to be A, so I'll just write it like that. To what these values might be. So we know that the initial value between A and B is 1,200. But we also know that car A is moving eastward at 35 miles per hour. Which means that this distance can be more accurately described in a rate of change scenario as 1,200 minus 35, that represents the miles per hour, times or multiplied by the time that it takes at each interval. So 5-hour interval, 20-hour interval, and 40-hour interval. So let's see, what does T represent here? T is obviously time, it's counting upwards. So just think about it as if 5 hours have gone by, and that entire 5-hour duration you were driving at 35 miles an hour. You know exactly how far you are from where you started. It would be 5 times 35. So the same kind of logic is happening here, but we're subtracting it from even more information, which is that they were originally 1,200 miles apart. B uses a similar logic, although it has no constant. We're not given the distance that B is going to travel or has traveled or anything like that. So it can, and remember this is A, it can simply be represented as 55, which is the speed that it's moving at, the miles per hour, times the time. That is our A, and that is our B. This is the equation that we're going to plug them into. And just to be consistent, the reason we're going to do that is because we're then going to take the derivative of that function, and that will tell us at each precise moment the distance between them. That's what makes this a question of related rates. Partially. Okay, so let's start plugging in variables to our equation. So we have C squared equals the value of 1,200 minus 35t squared plus the value 55t squared. We need to solve for c because that will allow us to take its derivative, which is what we're trying to find. Which means c equals the square root of 1200 minus 35t plus 55t squared. Does it? Hold on. Wait a minute. Okay, yes. And we want to take the derivative of this function. We could also take the derivative of this function. That's always an option, if you want to do that. Should we?
Either way, or you can even take a derivative of c squared equal to a squared plus b squared.
It's
Then
true.
you get c prime, a prime, and b prime.
Mhm.
Absolutely, either way is beautiful.
You will notice you start to have options in the way that you want to solve a problem like this. I'm going to choose to take the derivative of this function because I'd rather not deal with a situation that looks like this. Is that fair?
Yeah, absolutely.
Okay. If you're inclined, you can as well. If you're following along, just know that I've chosen something easier. So the derivative of this equation is 2c. And we're taking the derivative with respect to time because that's the information we're looking for. So dc dt equals 2 times, this is power rule, 1200 minus 35t. That's power rule plus chain rule. That's the inside function, it remains, but it's multiplied by the derivative of the inside, which happens to be 35. It's added to another chain function, chain rule derivative, which is 2 times 55t. That's power rule plus instant, I keep saying instant, it's inside function that remains the same, and it's multiplied by the derivative of the inside function, which is 55. Okay. To save time, we know that this is going to divide by 2c, so we need to divide this by 2c. Those cancel out. And again, for clarification, dc dt represents the rate of change at c. And for us, c is this distance, but the logic still maintains it. So it doesn't have to be a direct, remember it's the slope that we're tracking. It's starting to look like this because he's moving east. And that's the information we're looking for. So in order to solve this, we have to calculate c because we're currently solving a problem, and I was sort of encouraged not to do this, but it seems like I've done it naturally. To solve a problem that possesses two variables, and in order to do that, we have to think computationally, meaning that it's, a problem like this is happening separate from our solution, right? So we work on the solution, we come back to it, we get more information, we go back to the problem, we start plugging things in. That's sort of to be expected because we've been given a word problem as opposed to a formula to start with, looking for information. So how we think about it is just as important as how we choose to fix the problem. Right?
See, if you go with that original thing, c squared equal to a squared plus b squared you have, then that gives us c prime to a prime plus 2b prime. we can cancel those out. So C prime would be very much A times A prime, B times B prime divided by the square root A squared plus B squared,
Right.
which is exactly what you had. So the C prime we calculated was A, which is 35 times A prime, which is negative
35.
times 1200 minus 35t. Oh wait.
That's different than that.
Yes, no.
Is that correct?
No, what we did, you know the A prime. A prime is the speed, which is 35.
Right.
So 35 times A,
Times.
which A was 1200 minus 35t.
Mhm.
That's exactly what we have there.
That's right. T. Same logic went into 55.
Yes. 55 times 55.
55t times 55.
Yep.
And that is over the square root of what's in the parentheses plus 55t both squared.
It is a positive 35. Oh, it's not that you're going to the left. That 35 should be negative, because if you go to the left,
Right.
that's a negative value.
Yeah, because the derivative of this term is negative 35. And yeah,
All right, so
so that,
that's exactly what you have. So even if you go with the related rate problems, like, I mean, more than look at the relation, the rates between these three variables, exactly lead to the same thing you have. We were like, so we know the rate of change at the beginning is negative. Rate of change of distance. So the distance between the two cars is decreasing at the beginning. But we notice after like 5 to 10 hours, that negative become positive. So what we did was we graphed the C of t, the function for the distance between the two cars, and look what we got. And it's quite interesting because from the 0 time, look at the distance, getting closer, 10, 53, they get closer, they come as close as 1012, like minor feet, whatever the unit is, but then they start getting further away. Look at the distance, it's getting further and further away, which makes sense because car B is 55 miles per hour, the other one is 35 miles. So hopefully that gives you another glimpse what this does.
yeah, you see the downward sloping nature of this line. You can imagine you'd get a negative derivative as the tangents to these points would all be negative sloped.
Yes, excellent, yes.